welcome to the unit capacitors. So once again we're taking a historical perspective, and by now we have ended up in the 20th century, so almost a century. So in the 20th century, Robert van der Graaf, which in Dutch you would say Robert van der Graaf, who is from Dutch descent, designed the Van der Graaf generator, which we see in the picture on the right. So here you see a very large ball which accumulates many charges, and then thereby builds up a very high potential between the large and the small ball. So why do I show this to you in a unit about capacitors? Well, this is actually a very, if you want, poor design of a capacitor, because maybe you know typical capacitors actually look as we see the ones on the left. So what we'll show you today is why is this so much of a better design. Okay, let's refresh ourselves. Currents and charges. The current is the movement of charges through an area. So in this case, you see positive charges flowing through a tube with a current I, which is dq dt. If we have a closed loop, the charges move through the circuit and current keeps flowing because we have a battery or electromotive force that keeps pumping energy in the systems. And if we have, for example, negative charges, they will flow the other direction. So in this case, most of the time electrons float, so this is typically the direction electrons would take. But what happens now if we take away the resistor and we open the circuit? What we see is that charges will accumulate at the opening. Basically, the positive charges will accumulate on the top and the negative one on the bottom. Now remember, charges have an electric field. So here we see 2 point charges, a positive one with an outward electric field, a negative one with an inward electric field. In an open circuit, there can be multiple charges next to each other, as we see here. And now, if we add up the electric fields, what we see is that you get a constant or parallel electric field between the positive and the negative charges. And this is what a capacitor is. A capacitor basically consists of 2 plates very close to each other. And in the picture you see the circuit representation of a capacitor. 2 plates close together. If we look what happens at these plates, basically on the top of the plate you have positive charges, and for example in a negative you have on the bottom. And if the battery is put the other way around, you have the negative ones on the top and the positive on the bottom. So let's do some calculations. Remember that our potential difference, so the potential buildup between the 2 plates, is given as the integral of one distance to the other of electric field d over the distance r, so E dr. Because this field is constant, we can rewrite this integral as the potential difference is the electric field times the distance. Now, what we can see from this picture is the electric field scales with the number of charges you have per area. Imagine that you put 2 extra positive charges on the top, the electric field will become higher. Remember, if you can add up field lines. Now, you can rewrite this, putting the 2 together, and then what you see is that the potential differences scale actually with the number of charges times the distance divided by the area of the capacitor. So we can take that a step further, because if we know that the potential difference scales with the number of charges times the distance over the area, then we know that the number of charges that we can put in our capacitor scales with the area over the distance times the potential. Now we're getting somewhere, because what we see is that our charge is our constant times the potential. And this constant is what we call the capacitance. And this capacitance is given as the area times the dielectric constant over the distance. So if you rewrite that, you can say your capacitance is your charges per voltage. And the units are given by Coulomb, which is the unit of charge, over the volt, which is the unit of voltage, and it's given as farad. So it's 1 Coulomb per farad. And now you start to see why capacitors look like this. They have a very large area because they're basically a rolled up piece of metal, and in between they have a so-called dielectric material that makes the capacitance even higher. So if we go back, it's basically the dielectric constant epsilon, if you make that larger, you have a larger capacitance. So now we put a capacitor in a current. And you would think that if you put a capacitor in a current, you stop the flow, because that's what we saw before. But that's not really true, because imagine that if we have a current, which is our change of charge over time, and we know that our charge is our capacitance times our voltage, we can put the two together, and what we see is that our current is our change in DC, change in capacitance and voltage over time, which is basically, you could say, our current is our capacitance times the derivative of the potential over time. Because what you say here is that your capacitance is not time dependent. Because we know that our current is our capacitance times our dV dt, we can rewrite this to get our voltage. To go from a time derivative to the voltage, we take the integral. So what we see is that we can go from the current to a voltage by taking the integral and then finding out at every time point what the voltage is over our capacitor while it's either way charging or discharging. Okay, so now we understand the voltage behavior of a capacitor, but why would we even want to know that? So in this case, for example, where a capacitor is very useful is in the case of an electric car, where you want to bring your charges and your energy from your charging station to your car. You want to do this as fast as possible. So the more charge you have in your capacitor, the faster you can charge. But also, for example, in a case of a defibrillator, if someone gets a heart attack and you need to put a lot of charges very fast, you put a lot of charge in capacitor, and then by creating a very high voltage difference, you can release charges very fast and try to restart the heart. Well, I hope I triggered your interest in capacitors, and I wish you good luck with the rest of the units.